All right. Today, we're diving into one of the coolest frontiers in artificial intelligence. How in the world do machines learn to connect what they see with what they say? Let's get right into it. For you and me, this seems incredibly simple. We look at a picture, we describe it. But for a machine, this is a huge challenge. How do you possibly bridge that gap between a bunch of pixels and actual meaningful language? This is the fundamental question that drives this whole field. So, for the longest time, AI models were specialists. They lived in their own little bubbles. You had models that were geniuses with text, and you had other models that were wizards with images, but they never really talked to each other. The real revolution, just like with us humans, came from teaching them how to combine these senses. And that brings us to the core concept here, multimodal learning. It's the idea that instead of learning about, say, a cat from a million text documents, and then separately from a million pictures of cats, you train the model on pictures of cats with their text descriptions all at the same time. This creates a much, much deeper, more connected understanding of what a cat actually is. Okay, so how do you actually get these different senses to talk to each other? Well, some of the early attempts, called early fusion, just kind of jammed all the raw data together right at the beginning. It was messy and not very flexible. The much smarter approach, and the one that's way more common now, is late fusion. Think of it like this. You have an expert art critic and an expert writer. You don't force them to work together on a blank canvas. You let the art critic analyze the painting, you let the writer analyze the text, and then you let them combine their expert insights. It just works so much better. So this idea of combining senses was awesome, but it really needed a breakthrough moment to work at a massive scale. Researchers needed one simple but really powerful idea that could teach an AI the relationship between pretty much any image and any piece of text out there. And the big idea that unlocked everything? It was actually super intuitive. They decided to treat the entire internet's worth of images and their captions like one giant, epic matching game. The engine that actually drives this whole matching game is something called contrastive learning. The whole goal is to build a sort of map of meaning. On this map, the model learns to pull the correct image and text pairs really close together, while at the same time, it actively pushes all the wrong combinations as far away from each other as possible. Let's walk through how a landmark model called CLIP actually does this. It takes a huge batch of images and their captions. For any single image, its real caption is the positive pair. But every other caption in that giant batch, those are all negative pairs. The model's entire job, its only goal, is to get incredibly good at finding that one correct match out of thousands and thousands of wrong ones. Right, so how do you get really good at a game like this? Practice, and I mean a lot of practice. The original CLIP model played this game with 400 million. That's 400 million image text pairs that were just scraped from the internet. When you operate at that kind of scale, this simple matching game teaches the model a surprisingly deep and robust understanding of the visual world. And the payoff for all that hard work? It's incredible. The model gains this almost magical ability called zero-shot classification. This means you can give it a picture of something it's never been explicitly taught to recognize, like a specific type of bird, and it can still identify it correctly, just by figuring out which text description is the best match for the image. It's a huge deal. So CLIP really laid the foundation, right? But of course, the story doesn't stop there. The next big push in research was all about building on that breakthrough, making the models even smarter, more capable, and really importantly, way more efficient to train. You can really see the evolution here. First, you have CLIP, which totally proved the power of that massive matching game. Then came a model called BLIP, which made things even richer by not just matching, but also learning how to generate captions. And then BLIP 2 came along with an absolute game-changing trick for efficiency. Instead of building a whole new giant model from scratch, it figured out a really clever way to connect powerful models that already existed. And that amazing trick was something called the Q-former. You can literally think of it like a tiny, super smart translator. It sits between a huge pre-trained vision expert and a huge pre-trained language expert. Those big models are frozen. You don't retrain them at all. The little Q-former just learns how to make them talk to each other. This was revolutionary because it slashed the training cost and time. And here's the cool part. All of this foundational research didn't just stay locked up in a lab. It is the direct ancestor of the incredibly powerful creative AI tools that so many of us are using every single day. I mean, just look at text-to-image generation. You've got these two major paths, right? You've got the closed source, highly curated models like DALL-E 2 that you access through an API, and then you have open source models like Stable Diffusion, which anyone can download and run on their own computer. But no matter which one you use, the core technology underneath comes from these same ideas of connecting words to visual concepts. But creating images, that's really only half the story. The real magic, the next level, is when you integrate this visual understanding right into a large language model, allowing it to have a conversation about what it sees. And this is what gives us incredible tools like GPT-4 with vision. All of a sudden, the AI isn't just seeing an image, it's reasoning about it. You can ask it straight-up questions like, what color is the car? You can feed it a PDF and have it pull out data. It can read text from a sign in a photo. It can describe how different objects in a room relate to each other. It's a massive step towards an AI that genuinely understands our visual world. Okay, but with all of this amazing power comes a really, really tricky and persistent problem. These models, as incredible as they are not perfect. And their biggest flaw is something that researchers have a great name for: hallucination. So picture this. You show an AI a classic photo of the Leaning Tower of Pisa, and it comes back and says with total confidence, "Ah, a beautiful shot of the Eiffel Tower in Paris, France." That right there is a hallucination. The description sounds plausible, it's grammatically correct, but it's just factually wrong. So that's what we're talking about. A hallucination in AI terms is basically when the model generates text that sounds totally plausible, but it just isn't grounded in the visual evidence. It's either making up details or misidentifying things that just aren't there. And this, as you can imagine, is the #1 obstacle to building trust in these systems. So why on earth does this happen? Well, it comes down to a few key things. First, the language part of the model is just so good at telling a good story that sometimes it gets ahead of itself and makes things up that aren't in the picture. Second, the internet data it trained on is full of mistakes and bad captions. And finally, there's always going to be something lost in translation when you try to perfectly squash all the rich detail of an image into a few words. And that really brings us right to the cutting edge of AI research today. Because if an AI can look you in the eye, so to speak, and confidently tell you it sees something that doesn't exist, well, then the next great challenge isn't just about making these systems more powerful. It's about figuring out how to make them more honest, more reliable, and ultimately, truly trustworthy.